Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, International Telecommunication Union. Today, we're excited to host another webinar titled Integrated AI and Wireless for Sustainable Mobile Network Evolutions. Mobile networks have advanced through 5 generations, bringing significant benefits to society. However, the continuous evolution of these networks places a substantial financial burden on network operators. In this talk, we will unveil a new approach, unlimited vector processing, UVP, and a detailed overview of a RISC-V-based architecture and its customized extensions, which efficiently handles data parallel operations for AI and wireless baseband processing. But before officially kicking off the session, I would like to introduce our esteemed speaker, Zhiyuan Jiang. Zhiyuan Jiang is currently a professor at the School of Communication and Information Engineering at Shanghai University, and he's also the founder of Deep Transcend. His main research interests include wireless systems and domain-specific architecture. And as always, my colleague Vishnu, who will be taking care of the Q&A session. Now, without further ado, I would like to pass the baton to Professor Jiang. Now, Professor, the floor is yours.
Thank you. Thank you very much for the introduction, Jiaying. Let me first share my slides. Okay. Okay, is it good? Can everyone see my slides? I suppose it's good. Yeah, thank you. First of all, I want to thank Vishnu for organizing this event. I met Vishnu last year in Shanghai, and we had a meaningful discussion about the topic I'm presenting today. And since then, we are trying to work on this topic, and maybe in the future it can be more impactful. And also thanks for ITU AI for Good to organize this wonderful event. And okay, so today I'm going to talk about integrated AI and wireless for sustainable mobile network evolutions. So specifically, I want to talk about our design approach. It's an open source RISC-V domain specific architecture. So this can be seen as a preview of our work, because right now it's not completed. So I think in our maybe in July in our global summit in Geneva, we can unveil the whole project to the community. So today I want to give you a high-level picture of what we are trying to achieve by this design. My name is Zhiyuan Jiang from Shanghai University, and also Deep Transcend. I want to mention my collaborators, Li Min, Shi Yi, and so on. They are some of them are my PhD and master students, and Professor Shan Cao is my colleague in Shanghai University. Professor Sheng Zhou is from Tsinghua University. And our lab is this lab is the Advanced Communication and Computing Electronics lab. So this is our introduction. So today I want to talk about some background and motivation. This is a very important part because I want to give you why we want to do this project, and then some related works. What other people are doing? What is the other approach? What's the alternative? And then I will introduce 3 of our projects, namely ICO, Venus, and Zoozve. They are the combination of them is the whole stack of our work, from open source library to toolchain, compiler, and then to the chipset, the hardware. That is a whole stack. Okay, the first is background. So I will introduce some different aspects of the background. I want to make you up to date of we are on the same page of what's happening in today's wireless mobile network and AI community. Okay, so we all know that our mobile networks have evolved tremendously over the last 20, 30 years. In 2010s, we have the 4G. 4G is very important because after 4G, we cannot have this mobile internet or mobile network. We can do all the things by our cell phone. So 4G is kind of very important for our mobile network. After 4G, we have the 5G. The 2020s. After 2020, we have massively deployed 5G in our society, and maybe after 5 years, we will have 6G. Right now, we are developing namely 5.5G, the 5G advanced. This is the standard we are developing. And in 5 years, in 2030s, we will have the 6G. Okay, so what's driven this constant evolution of mobile networks? The 5G, the generation we are currently using, is mostly driven by performance improvement. Because in 4G we have many applications, but in 5G we don't have enough applications, but we want to have more performance. For example, the data rate, the reliability, the energy efficiency, the latency. We want them all to be better than 4G. This is performance driven. But after 5G, in 6G, we want to focus more on applications in scenarios because eventually we want to have our mobile networks to be profitable, to have better applications. So from IoT, Internet of Things, or Internet of Everything, in 6G we will have intelligent Internet of Things, the IoT. Okay, this is the driven force. But behind all this, we want to be honest about ourselves. So the constant evolution of mobile networks have put a lot of stress on the operators and on the society. I want to apologize for some of the texts because they are in Chinese, because I want to give you some feedback from the Chinese market. The first aspect is from users. the users cannot feel the real evolution of mobile networks in 5G, because in 4G, we can, for example, we can order food from by our cell phone. In 5G, we can also order food by our cell phone. Maybe the latency is slightly shorter, smaller, but we cannot feel the real killer application. So many people argue, many people complain, the users complain that we pay more on 5G, but we don't have more experience on 5G compared with 4G. On the other hand, from operators, the operators are more, I won't say more unwilling to evolve from 5G to 6G, because there are reports that, for example, China Mobile has investigated the 5G investment, and they say that the investment of 5G is so large that maybe 20 years from now, it cannot be even, cannot make even by the operators. So why do we want to have 6G with a lot of new infrastructure, a lot of new investment, when our 5G is still not even yet? So there are some reports saying that, for example, the 6G threatens to be the mobile lost generation, and Vodafone's network strategy director has said that maybe nobody needs 6G. The industry should make 6G a no-G. And other experts said that they hope that we don't have to have 6G. We want to have the 5G as our last generation. This is all from the operator's point of view, because the financial burden of constantly evolving mobile networks is so high that it cannot be sustainable. So that's why it's called the sustainable 6G evolution dilemma. Okay, so more background. So that is the dilemma. And also, I want to mention the background that in 6G, mobile network is tightly integrated with AI, because if you read any newspaper or watch any news on TV or internet, you can feel that the current big wave of AI technology, the ChatGPT, the DeepSeek, all the technology in AI have driven and made our life very different from before. So this is the same scenario with mobile networks. Mobile networks in 6G will be tightly integrated with AI. There is AI for network, meaning that we can use AI to optimize our network, and network for AI, because we can use network to make AI more efficient. Anyway, the network and the AI will be tightly integrated, and the people use the mobile network to access AI, and the network will use AI to optimize itself. And there is a tremendous trend, namely the AI Run Alliance. Okay, so AI Run Alliance was established on February last year. So basically, AI Run is using AI chips, in this case, the NVIDIA GPUs, using the AI chips to reconstruct or revolutionize RAN. RAN is the radio access network. So in this way, we use GPU to replace all the hardware in the RAN architecture and in the base stations, in the core network. We use GPUs instead of the DSPs and the FPGA previously. Okay, using the GPUs, we can make the base station run AI algorithms very efficiently. In this way, we can use the base station as if it is a big AI server. And also it can do baseband processing because GPUs have very powerful computing capability. So NVIDIA and SoftBank have proposed this idea and have an alliance with, for example, there are many vendors like Nokia, Ericsson, and many others. And also there are Microsoft, T-Mobile, the operators, and so on. Many companies have joined this alliance to join this trend. And there is some news saying that there will be more than 200,000 base stations built in this way in Japan or worldwide. Okay, this is the AI Run Alliance. Okay, so I want to also mention the traditional run architecture because the AI run and the architecture we are proposing is very different from today's run architecture. So what is, for those of you not so familiar with mobile networks, I want to mention what's the traditional run architecture in today's life. If you look outside your window, you may see a base station, and 99% of that base station is this. The current architecture is like this. So traditional run is the proto stack of wireless signal processing and the mobile networks. The proto stack is runs on proprietary hardware, meaning that, for example, I am China Mobile and I bought a base station from Huawei, and then Huawei provide a proprietary hardware and software for me, and then this base station can work. And the radio unit and the BBU are connected via proprietary interfaces. They are all provided by the vendor. Okay, the single vendor provides both radio unit and BBU. This is the traditional run architecture, and the baseband in the physical layer of wireless communication is called the baseband. The baseband is responsible for all the signal processing in the wireless modem. So traditional baseband is usually DSP plus ASIC architecture. DSP means digital signal processor, and ASIC is application-specific integrated circuit. So this architecture, the core processing unit of the baseband is solidified by the hardware, and the software and the hardware is closed, meaning that each company have its own solution, software and hardware solution. So they are not open source. By not open source, we are using the closed ecosystem architecture. It's very different from today's, for example, AI community. In today's AI community, you can almost use everything as open source. For example, DeepSeek is open source, and there is a strong trend towards open source in AI community, which is very different in mobile networks, because in mobile networks, most systems are closed. It's not open source. You cannot access the software of base station anywhere. Okay, so this is the traditional architecture. So I want to summarize my background because I understand I have mentioned quite a few things in my background. So I want to summarize and give you the whole idea how these dots are connected together. Okay, so from the industry side, especially the operators, they are thinking that the 6G and the 7G and the 8G, maybe MG, right, XG, in the future, this trend cannot go on forever because it's not economically sustainable. It's not like, for example, in a city we build roads, and more people means more road. I just have to build more road for the city. It's not like this, because in the mobile networks, when you have 4G, you have more people using the network. You want to have 5G and 6G. You have to replace all the hardware, all the base stations from 4G to 5G. And this investment is so huge that it's not economically sustainable. This is from the operator side. And then the other thing, the operator is very concerned or wish to change is that the operator, they are vendor locked, meaning that if you buy from one vendor, for example, Huawei, you cannot change the software, and if you are smart, you use a more advanced algorithm. You cannot just change the algorithm in the base station because it's not visible to you. It's a black box. So there is limit flexibility and scalability in RAN. This is from the industry side. And also there is another strong trend towards AI-driven network because AI is very important. Everyone agrees with that. So next generation of mobile network must be AI native, meaning that the network itself must be intelligent and have sophisticated AI algorithm run on the network. And but if you think about it, the AI community is very different from the mobile network community. AI community is very open. Everything is open source, but the mobile networks are very closed. So the hardware choice is very limited, and the open source platform is very limited in the mobile network community. This hinders the hardware efficiency and the cross-domain innovation in mobile networks. And also from academia point of view, it's also not so good right now because you are lack of open source reference and designs, and it's very hard to design a new algorithm and then push the algorithm, apply the algorithm on the commercial hardware because the time to market is very long. So from the academia point of view, the current system is not very friendly to new algorithms and the new architecture. So it's very hard to integrate cutting edge research and industry feedback for the current network. So in summary, we want to say that sustainable mobile network evolution is a major challenge. So our solution lead to our thinking that we want to have an open source, decoupled software and hardware, meaning that you have a hardware that can do various kinds of things very efficiently. Then your software can be built, can be open source and run on this hardware, so it can be more white box. You can see your algorithm. You can see everything run on the software on the base station and on your mobile phone. This is very different from today's architecture. And we also want to have an integrated AI and wireless chipset, meaning that the computing unit, the very fundamental of the computing resource on the chip, can be shared between wireless baseband and AI processing. In this way, our chip can be very efficient in doing both things. Okay, so this is the background, and I want to mention some related works because there are also some other approaches or some endeavors towards this direction. The first one is kind of very well known in our community, the Open RAN, ORAN, or VRAN, virtual RAN. So the ORAN idea is that instead of the traditional black box approach in the left hand side, we want to have a more open approach. This open meaning that we want to have decoupling of hardware and software and unified interfaces. By decoupling of hardware and software, in the ORAN, usually the decoupling of hardware and software means that you use general purpose, for example, X value x86 servers to run the software, and the hardware is just a general purpose CPUs. In this way, you can run any software on these CPUs, but the efficiency is not so good because you know that the CPU is not very good at parallel computing. In this, because of this, the baseband function is not so good on general purpose CPUs. Okay, this is the decoupling of hardware and software. The unified interfaces, meaning that if you define this interface, for example, the RU and the DU, the interface between RU and the DU, if you define this interface to be standard or let's say universal, then you can replace your RU with another vendor, another company, and using this standardized interface, you can communicate with your DU. So this is the approach or the approach to have different vendors to play a role in your base station. Okay, this is ORAN and VRAN, and also there are some open source wireless community. For example, the open air interface. It uses CPU plus FPGA or GPU to have. This is an open source library. You can download the library online, and the OAI is a library that have quite complete 4G and 5G prototype running on CPU and FPGAs. Okay, this CPU is also general purpose x86, those kind of CPUs. Okay, this is open air interface, and also there's other platforms like SRS-RAN. It's also an open source project, also running on general purpose CPUs to have this kind of open source libraries of software defined radios in the system. Okay, there are also some other companies doing proprietary solutions. For example, Amerisoft is a company that use proprietary proto stack to produce simulators and testing equipment for industry and the lab. Use software to simulate the behavior of many users and then connect it to the base station so that the base station can be tested by this equipment. The problem is that it's also the ecosystem is closed and AI is not supported. Okay, so AI run is like I said before, is run by NVIDIA and SoftBank, and the alliance also has other companies. Basically, AI run is built on GPUs. GPU is very powerful. Everyone knows that. It has enormous computing ability, so it can run AI algorithm and baseband very efficiently. But you know, GPUs are very expensive, and it cannot be used everywhere. For example, in base stations or in your cell phones, because it's very expensive, and also very power hungry. It's power consuming, right? So AI run is using GPUs. So I want to compare our work with the related works I just mentioned. So OAI and SRS-RAN and Amerisoft, they are all run on general purpose CPUs like Intel's x86 CPUs. And AI run is run on GPUs, the NVIDIA's GPUs. And the current traditional approach is using modem plus NPU. NPU is neural processing unit. In this way, it's all ASIC. You know, it's all application specific IC. So in this way, the cost is very low and the efficiency is very high. But the problem of modem plus NPU is that it is closed. You cannot, there are no open source library in this regard. AI run is open, and also OAI and SRS-RAN, they are naturally open source. But their efficiency and power, energy efficiency, and the cost They all have limitations. So what we are trying to propose is that first of all, we want to have an open source ecosystem, meaning that you can program your wireless devices down to for example, the decoder, encoder, modulation, demodulation, the very basic physical layer implementation. You can reprogram, and it's very open source. It's visible to all to users and operators. Visible to everybody. So this is first of all, we want to have an open solution. Second of all, we want to have almost as good AI and baseband performance as the best. Like for example, in AI performance, we think NPU and GPU, they are very good. And the baseband performance, we think ASIC modem is very good. We want to have an integrated AI and the baseband chip so that they are almost as good as the best. But we know that it's not optimized for either of them, so it cannot be both best at AI and baseband. So we want to have almost as high as them. And the energy efficiency is very good. We want to have better energy efficiency compared with GPU and CPUs because they are domain specific architectures. Okay, so the cost is also low because we don't have to have the computing power of a GPU. We don't want to do server, like for example, we don't want to be an AI server. We just want our chip to run some AI algorithms and the baseband algorithms on our chip. So this is our solution. Okay, I will go into some details of our solution because I realize I don't have enough time for everything in this talk. So I want to give you some basic ideas of our solution. So this is the pyramid of our solution. Our solution is kind of a vertical integration of several projects. We have conducted, I think, from 2020, like 2021, or almost 5 years, we have built this pyramid. So on the bottom is our chipset design. We call it Venus. Okay, this is the chipset architecture. It's a RISC-V-based domain-specific architecture, and also multi-core data flow-driven architecture. And this is for integrated AI and wireless baseband processing, WBP. Okay, we have our multi-core architecture, our micro architecture, and our silicon. This is Venus. And built upon Venus, we want to have our toolchain. Because you know the problem with RISC-V and its extension is that it cannot have, it doesn't have as good as the toolchain of, for example, ARM or x86 CPUs. They don't have as good as the toolchain of other architectures. We need to have our own toolchain or compiler, those kind of or operator, those kind of things. So this is what we call the Zoozve. It's actually a subplanet of Venus, so we call it Zoozve. This is our toolchain, and built upon our toolchain, we have our applications. ICO. ICO is a library, is an open source library for 5G, 4G. And also, surprisingly, we also have GNSS. I will talk about this later, okay? This is also open source, okay? This is ICO. So combining with all of these architecture projects together, we want to build an open source, fully software defined and evolvable AI integrated mobile network baseband architecture. And also its toolchain and open source library. Okay, this is our solution in one slide. Okay, so I will go into some details of each of the projects. The first one is ICO, because I think ICO is more understandable to normal audience. Even you don't know anything about chipset or toolchain, or compiler, you can understand what we are doing by this ICO library. So I will first introduce ICO, then go into more details in Venus and Zoozve. Okay. So ICO is if you mention ICO, you must also mention Venus, because Venus and ICO is like ICO is software and Venus is hardware, and they are connected together by Zoozve. So together, Venus and ICO, we have a software hardware fully decoupled solution designed for AI native wireless baseband. Combined with those, we have better baseband performance compared to GPU's AI run, and better flexibility, much better flexibility compared with DPU, DSP plus NPU, because in DSP plus NPU and other accelerators, you cannot use the 4G devices for 5G applications, because in 5G we have different signal processing approaches. The polar coding, the LDPC coding, they are very different from 4G. If you have dedicated accelerators, you cannot a software upgraded from 4G to 5G. But in Venus and ICO, you can do this because it is fully software defined and evolvable. In GPU, you can also do that because GPU is also general purpose. You can use different software, but the GPU is very expensive and very power consuming. Okay. So ICO is a free open source software, very easy to program because we use C with the addition of Venus instruction set. It's basically you can use C to define your baseband, to program your baseband. This is very simple and easy to program compared with Verilog or other VHDL. If you want to have a silicon or FPGA to do the baseband processing, okay, this is very easy to use. Okay, so you can. This is some of our simulation results. You can, if you look at the right figure, those blocks, FFT, channel estimation, channel equalization, they are already written in our open source library. You can just take them and construct them together and connect them together. You can have a whole baseband function chain. And if you simulate the performance, you can see that our performance is better than AVX. AVX is Intel's SIMD extension, and the Neo is ARM's SIMD extension, and the TI-64X is DSP. So we have better performance compared with these architectures for typical wireless applications, for example, FFT, channel estimation, and also for AI examples like 2D convolution, max pooling. Those are very common convolution neural network operations. Okay, so with our ICO approach, you can prototype your AI native wireless network very efficiently, because we have a simulator that can give you an idea of how much time it takes to process this these signals in our hardware. We have a simulator to do that. So using this kind of simulator, you can have an idea of the efficiency of your programs, of your signal processing blocks on the hardware. Okay. So compared with previously, if you have a new function, if you are academia student, you want to have a new algorithm and you want to apply in the current base station, you will have to first design the algorithm, and then if you want to have a silicon a chipset to realize the algorithm, you must design the RTL, the FPGA prototyping, and then if everything goes well, you can tape out your chip. And after several months, and with very good luck, you can have a good chip that can realize your algorithm, and then you give it to the vendor company, and using this chip to realize your baseband function. This is very time consuming and very hard. Okay, so in our approach, you can use the ICO open source library and then design algorithm and realize it on our Venus chip, and then you can use this chip as your product, and give it to the vendor to realize this algorithm. This is very simple, and also very efficient, because our design realize the various baseband processing units with very high efficiency compared with CPUs. Okay, so I will skip this slide and give you an example of how you program. This is an example of how you program a QPSK demodulation using the ICO, using our open source library ICO. Okay, so you can see that it's basically the standard C, and using some instruction designed by our library, for example, V-range, V-shuffle, V-add, those kind of instruction. You can decompose your algorithm into this kind of operations, and using the instruction to represent its operation, and then you have a signal processing block doing the PBCH demodulate of current mobile networks. Okay, so first you write this kind of task, and every task can be written in that way, and then you just have to connect all the tasks. For example, if you want to decode PBCH signal from current 5G mobile network, you can use this kind of we call it DAG. It's a directed acyclic graph. You can use this kind of graph to connect those tasks together using the code shown on the left side, and then this DAG can process the PBCH decoding in the Venus chip. Okay, and then after this processing unit, the DAG, you just also have one more thing to do. You have to configure the I/O1 scheduler to write a I/O1 scheduler file to deliver the DAG level task to control hardware interrupts and the data transmission with the digital front end. After this, you can have a baseband chip that can do baseband that can do PBCH decoding in your chip. And we also have other features. For example, we can handle peripheral interrupts. We can handle DMA interrupts and analyze DAG return values and control DMA transfers. Okay, so this is an example, and we are working on more and more library using this kind of software. Okay, let me see if okay. So I must hurry. Currently, we have this architecture ready, and we have to have more libraries ready by the end of July. Okay, this is our operator library. For example, we have FFT, BP decoding of LTPC, coding, and also other IoT and NR related processing blocks and AI blocks. This is our experiment using our devices to decode the real world mobile network signals. Okay, so I want to have a teaser or preview of what we are trying to do and present on the global summit in July in Geneva. Okay, so first we want to have our 5G and 4G proto stack almost ready, and we currently we have the PBCH channel. We want to have like our random access procedure and other related RC signaling ready by the end of July. Additionally, we also have an open source library for GNSS, the GPS, and BeiDou in China. And those GNSS baseband, we have that almost ready and to be released in July. Meaning that using our Venus chip and Echo open source library, you can have a fully software-defined and open source GNSS baseband. This is also, I think, it's first in the community. Okay, we also have a LoRa open source library, because LoRa is compared with 4G and 5G is very simple. The baseband is very simple. We can have that as our backup, and the other wireless proto stack. Okay, this is what we are trying to do, and also we want to tape out our chip by the end of July. Okay, this is the GNSS, because currently we have the GNSS baseband and RTK positioning realized on FPGA. The next step is transfer those hardware language FPGA to Echo. Echo is software defined. It's based on C language, so it's we have that operating on FPGA. We want to transfer it to the Echo open source library. This is our work. Before the end, hopefully before the end of July, we can have that ready. Okay, so I think I have a little time for our more in-depth architecture of Venus and Zoozve. I think that's okay, because I don't think many people can understand those that much of content in such a short time. So I want to give you a high level idea of the Venus hardware architecture and the toolchain Zoozve. Okay, in Venus we built a cache-free many-core architecture to deal with wireless baseband processing and AI-related signal processing. So we developed a pack and ship data dispatch system to enable very efficient memory access. Because in chipset design, especially in this kind of very high data volume chipset design, it's better to have very good memory access time compared with other design. Okay, so we have a hierarchical data flow task scheduling scheme with multi-threading and lazy deletion, many schemes, so that the efficiency of our design is very good. Okay, so this is in comparison with other architectures. Currently, many cell phones and base stations are using the DSPs. DSPs are very good at VLIW. VLIW is a very long instruction wise. It can have a very VLIW can boost the instruction level parallelism, but the compiler is very complicated in the VLIW design. So DSP is I think DSP is kind of the traditional way of wireless baseband processing. Currently, many people are investigating using GPU, GPU, general purpose GPU, using GPU to do wireless baseband processing. But GPU is first of all, it's very expensive, and the second one is very power consuming. So this is not a good choice for massive deployment. And also we have the ASIC. ASIC is have very good performance, but it's a very long time to market, and it takes a lot to develop, and it cannot be software upgraded. If you have a 4G, basically you cannot do 5G applications. Okay, so our work is comparison with other works in the literature. We have the bottom line is ours. So we have in summary we are very good. Okay, so if we are not good, so we will I will not do this slide. Okay. Okay, I think I don't have the time to go into details, except to say that we are a RISC-V-based tile and multi-core architecture with NUMA, the non-uniform memory access architecture, and a pack and ship approach, so that the data is localized. We don't have to go very far to reach for the data in the DDR or those kind of memory. So we have a very good memory access, and we can do heterogeneous configuration, and we are a data flow model. Data flow model means that any time a date is ready, we can fire those tasks instead of the traditional phenomenon approach that you must follow instruction flow. Okay, this is the data flow model. Okay, so we also have the multi-level scheduling. I'm sorry that I don't have to go into all the details. This is also scheduling. So because we have multi-core, we must schedule the tasks to the different cores. This scheduling is performed by our multi-level scheduling approach. Okay, this is our evaluation results compared with GPU, ASIC, and DSP and hardware accelerators. Our performance lies between commercial hardware and ASICs, meaning that lies between DSP and ASIC, because ASIC is designed specifically for this kind of task. So it has the best performance, but it cannot be software defined. Okay, so our performance is not as good as ASIC, but we want to say that we are close or similar with ASIC, but we have better software definability. Okay, this is other evaluations, and this is our FPGA prototype using current mobile network standardization. It's a polar code in the 5G CCH channel. Okay. Okay. So that is our baseband chip architecture. The Zoozve is our compiler. You can think of Zoozve as the GCC or ARMCC in that regard. So we want to have a compiler that can do efficiently on our design. So in this way, we design Zoozve to be a strip mining free RISC-V vector extension compiler. So by strip mining free, we mean that this is a concept in the vector processing community. Is that if you have a vector processing unit, you process a long vector, but after some iterations, you may realize that you have some elements left to process, but you don't have the or you have too many processing units for this small set of elements. So you have to do strip mining. So that's a lot of overhead. So in our compiler design, we want to have a strip mining free compiler support. So in this way, we can see that using our compiler, we can achieve almost 300% speed up by dynamic instruction counts for FFT and other operations. For example, the dot operation and AXPR. AXPR is just the AX plus Y, this kind of vector operation. Okay, so we all achieve very good performance compared with compared with standard RVV. Standard RVV is a RISC-V vector extension. It's the standard vector extension of RISC-V. So using our compiler and the Venus architecture, we can achieve much better results than the standard. Okay. We also have a heterogeneous compilation support on our platform. Using this, we can achieve integrated AI and wireless compilation support, meaning that we have a unified programming model for both wireless and AI tasks. You don't have to use because traditionally wireless and AI, they are very different programming model. AI use, for example, PyTorch or Tensor, and the wireless you use ASIC, you use Verilog, and the DSP you use C. And in our design, we also use C. But in the by this compilation support, we can use a unified programming model for our wireless and AI. So for the programmer, for the developer, it's unified. You are very convenient. Okay. So we also put this into evaluation and achieve some good performance. Okay. So to summarize, okay, this is the last slide. Okay. So to summarize, we want to mention that there are huge concerns over inefficient investment on mobile networks going forward in 6G and in the future. Okay, the integration of AI and communication is a major trend that I think everyone can get on board with. Okay, so by these two very strong motivations, and we do this work because the current work has limitations of baseband chip architecture and ecosystem. And this intensified the concern about the ability to support the continuous evolution of mobile networks to support native AI-driven mobile networks. Okay, so our study, we propose a scalable, software-defined, AI-integrated, and sustainable baseband chip design, and our compilation support, our compiler, and our open source library. We hope that to release and make the open source library public by the end of July in the global summit. I think that's a very good very good time point in our design, because I think you need to have sometime you need to have a deadline to push you. Okay, so I think the end of July can be a very good deadline for us. So we want to make the open source library public by that time, and in that way we can have open source 5G and also GNSS and also LoRa protostack and some AI models available. Okay, so thank you very much. That's all I can talk about in this webinar. And if you have further questions, you are more than welcome to send me an email at this address. And I also want to thank again for the AI for Good community and also my collaborators to contribute in this project. Thank you.
Thank you very much, Juan. This is a wonderful talk, and maybe we have a couple of minutes with quick questions. Actually, George is asking, would this work with 4G, especially the eco application framework that you have? Would that work with 4G? And
yes.
Also, yeah, go ahead.
Yeah, it's it can work with 4G, even 3G and 2G. It's fully software defined. So you can currently we have 4G and 5G, and I think it can also have any G you want, as long as the computing capability is okay. Because in 6G maybe you have a very very complex algorithm that our chip cannot support, then it cannot run 60 or 70. But you can always count on the if we have more money, we can have a more powerful chip. Then it can do 60 and 70. Yeah, definitely can do 40. Yeah.
Wonderful. And the another question is, where do we get this? I mean, how do we get this Venus, Eco, and Zoozve platform? I believe you already answered it. In July, we probably, hopefully, we announce this availability and also make it available. So I think that is very clear. I want to ask maybe a quick question about AI integration. You mentioned about AI integration and the compiler framework integration. That's very interesting. Other than the compiler framework integration, is there anything else that makes it AI native to deploy or to use AI?
That's a very good question, because if you use AI models today, you are probably using CUDA, the NVIDIA proto stack of AI models. So CUDA has done a lot of job. It has a lot of operators written by all kinds of experts from all over the world over the year. So currently in our AI toolchain, we can only support the often used operators. For example, the 2D convolution, the max pooling, the average pooling, the transformers. Those operators are widely used. We support that, but we cannot say we support every kind of operators like CUDA, because takes a lot of time, and that is the reason we want to make it open source, because we want to attract more people to develop the operator repository, because our own self cannot do all the work.
Yeah, I think that's where we like to have a good collaboration with you. I think it's truly interesting, like we discussed previously in Shanghai as well. It's very interesting the way you have disaggregated the architecture, especially for baseband, and made it open source along with the AI native architecture. We hope to see you in Geneva with a launch announcement, and we hope to work with you for this in coming years. Yeah, thank you very much for taking the time and staying late. Back to you, Jan.
Thank you so much.
Thank you. Thank you, Vishnu, for the Q&A session, and thank you, Professor, for your contribution during the whole talk. I would like to now thank everyone for watching this webinar today. We encourage you to stay until the end and interact with our speaker. And we also have more interesting talks in the future, so please check the AI for Good program page for more details. We look forward to seeing you in the future. Thank you for joining, and have a nice day.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.